Hi there, and welcome to this lesson on Pure Mathematics 4. In this lesson, we're on Chapter 7, 7.4, and we'll be considering vectors in 3 dimensions. A 3-dimensional vector is described by adding a third direction z, which is perpendicular to both the x and y axes. To visualize this, the origin is a little bit like the corner of a room, and the space between the x and y axes, that would contain the floor of the room. And the z-axis would be taking you up one of the walls. We think about a vector, OA. It can either be written as a column vector, adding a third number z, x, y, z, or it can be written in ij and k notation, adding the third letter k for the z direction. And that would give us the vector OA is equal to xi plus yj plus zk, where I is the unit vector in the x direction, j is the unit vector in the y direction, and k is the unit vector in the z direction. Okay, position vectors. Consider 2 points, A and B, which have got coordinates 2, 3, 5 and 4, 5, 1. But first of all, before we think about position vectors, a little think about sketches, especially 3-dimensional sketches. The axes don't help. They do just make the whole drawing look more confusing. So if you're going to make a sketch, don't draw the x, y, and z axes. Just label the origin O. So we'll get rid of the axes, keep the origin, and the sketch simplifies a great deal. Okay, position vectors. The position vector of A is the vector OA. It's the vector which starts at the origin and ends at A. Position vectors are extremely similar to coordinates. If you think about the coordinate, A, 2, 3, 5, those are the coordinates of a point in space. If we think about the position vector OA or A, it's exactly the same numbers, and it always is. So the position vector is also 2, 3, 5. It's the position vector of A, and it's really telling you how you would get from the origin to A. But the concept is extremely similar to the concept of a coordinate. And really, in most questions, you can think of them as being identical. Coordinates, position vectors, they are essentially the same thing. If you know the position vector of any 2 points, then you can find the vector between those 2 points. So if we think about the vector between A and B, it would be AO plus OB, which is minus A plus B, or B minus A. And that always works as long as you know the position vector of the 2 points. So the position vector of AB, not the position vector, sorry, the vector AB is equal to the position vector of B, take away the position vector of A. This is extremely important in work on vectors. It gets used all of the time. The vector AB is equal to B minus A. Okay, let's have a look at an example. Let's say the position vector of A is OA, and the vector AB is B minus A. Find the position vector of A and B in ij and k notation, and then find the vector AB, both as a column vector and in ij and k notation. This isn't really adding very much to anything you've done before, so don't overcomplicate it. It is straightforward. Have a go, pause the video, come back to me when you're ready. Okay, let's have a look. So first of all, the position vector of A, OA, that's just 2i plus 3j plus 5k. You take the numbers from the coordinates and just change it into a vector. And similarly for the position vector of B, OB, you just take the numbers from the coordinates, and that gives you the position vector of B, 4i plus 5j plus 1k. And then the vector AB is equal to the position vector of B, take away the position vector of A, which is 4, 5, 1, take away 2, 3, 5. So the vector AB is equal to 2, 2 minus 4 as a column vector, or 2i plus 2j minus 4k in ij and k notation. Example 2, given that A is equal to 2 minus 2, 0, and B is equal to 3 minus 1, 2, prove that 3a plus 2b is parallel to the vector 3 minus 2, 1. Now, in a previous lesson, we learned that if two vectors are parallel to each other, then one of them should be a multiple of the other one. So that's what you're trying to do here. You're going to work out 3a plus 2b and show that it's a multiple of the vector 3 minus 2, 1. I'll let you have a go at doing that. Pause the video. Come back to me when you're ready. Okay, let's have a look. So first of all, we need to work out 3a plus 2b, which would be 3 times that plus 2 times that. Multiplying out the brackets gives us that. Adding them together gives us 12 minus 8, 4. Now 12 minus 8, 4 is 4 times by 3 minus 2, 1. 4 3s are 12, 4 times minus 2 is minus 8, 4 times 1 is 4. Therefore, 3a plus 2b is parallel to the vector 3 minus 2, 1. It goes in the same direction, but it's 4 times as long. To find the magnitude of a vector in 3 dimensions, we still use Pythagoras. It's the 3-dimensional version of Pythagoras. So the magnitude of x by z is equal to the square root of x squared plus y squared plus z squared. And if you're asked to find a unit vector, same method as before, it's the vector divided by its magnitude. So x, y, z divided by the square root of x squared plus y squared plus z squared. Bearing that in mind, have a go at example 3. Given the vector a, 2, 3, 6, first of all, find the magnitude of a, and then find the unit vector that goes in the same direction as a. I'll let you have a go at doing that. Pause the video. Come back to me when you're ready. Okay, let's have a look. So to find the magnitude of a, we use Pythagoras. So it's the square root of 2 squared plus 3 squared plus 6 squared, which gives us that, which simplifies to root 49, which is exactly 7. And then part 2, to find the unit vector in the direction of a, we just do the vector divided by its magnitude. So that's 2, 3, 6 divided by 7, which just means we need to divide all of these numbers by 7. And that would give us the unit vector is equal to 2 over 7, 3 over 7, 6 over 7. Okay, we can calculate the angle between a vector and each of the coordinate axes by using trigonometry. Things start to look a little bit complicated. So we'll be finding the angle between the vector and the x-axis, the angle between the vector and the y-axis, and the angle between the vector and the z-axis. So theta x, in terms of notation, that means the angle between the vector and the x-axis. And this is a right-angled triangle we've got here, and we can work out that angle just by using trigonometry. So the cosine is adjacent over hypotenuse. The adjacent side is this one here, which is the distance in the x direction. The hypotenuse is the magnitude of the vector. So the cosine of the angle, and that's the angle between the vector and the x-axis, is equal to the x value divided by the magnitude of the vector. Something very similar happens if we want to find the angle between the vector and the y-axis. It's the y value over the magnitude of a, will give us the cosine of the angle. And for the z-axis, it's the z value divided by the magnitude of the vector, and that'll give us the cosine of the angle. Okay, let's see if you can make sense of what all of that means. So example 4, given that P and Q have got position vectors 7, minus 2, 4, and minus 1, minus 4, 3. First of all, find the angle between the vector P and the x-axis. Then find the angle between the vector Q and the y-axis. And then prove that the triangle OPQ is an isosceles triangle. I'll let you have a go at working your way through that question. So pause the video, come back to me when you're ready. Okay, let's have a look. So first of all, the angle between the vector P and the x-axis. So the cosine of that angle is equal to the x value divided by the magnitude of A. Now for P, the x value is 7. And then the magnitude of the vector, so the vector p in this instance, would be the square root of 7 squared plus minus 2 squared plus 4 squared. So the cosine of the angle will be 7 over root 69, and that gives us an angle of 32.6 degrees between the vector p and the x-axis. Part 2, we do exactly the same thing, but this time with the y-axis. So the angle between q and the y-axis, we'll need the y value from q, which is minus 4, divided by the magnitude of the vector q, which is minus 1 squared plus minus 4 squared plus 3 squared, square rooted, which gives us minus 4 over root 26, which means that the angle between the vector and the y-axis is 141.7 degrees. There's no problem with the angle being greater than 90. And then part 3, we're asked to prove the triangle OPQ is an isosceles triangle. Well, the easiest way to do that is find the 3 lengths of the sides of the triangle. We need 2 of them to be the same as each other, and we need the third one to be different. If that's the case, then triangle OPQ must be an isosceles triangle. So first of all, we need to find the length of PQ. Well, that means we need to find the vector PQ. The vector PQ is Q minus P, which is minus 1, minus 4, 3, take away 7, minus 2, 4, which gives us minus 8, minus 2, minus 1. We then need to find the magnitude of that, how long it is. Using Pythagoras, that gives us the square root of 69. Then we need to do the same thing for OP. The vector OP is just 7 minus 2, 4. It's the position vector. And the magnitude, again, we use Pythagoras, and that also gives us the square root of 69. We do need to check the third side, because it could be an equilateral triangle. And OQ, that's just the position vector of Q, and the magnitude of that is the square root of minus 1 squared plus minus 4 squared plus 3 squared, and that gives us the square root of 26. So 2 of the lengths are the same as each other. The third length is different. Therefore, triangle OPQ is an isosceles triangle. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 111 and have a go at exercise 7D. Thanks very much for listening, and cheers.